different ways that these radioactive isotopes try to stabilize themselves. And they're radioactive because they're unstable. All right? Basically, we've got, I think you asked me this yesterday, up to element 90. Some of those have natural, it was either 90 or 93, are naturally occurring isotopes, and isotopes do occur in nature. The periodic chart is actually a running weighted average of all the isotopes that exist within an element. So carbon-14, if I look at carbon-14, as an isotope, it's written like this, with the atomic weight on the top and the atomic number on the bottom. Or you may see it as carbon-14, or all that means is that out of all the possible carbons that exist, this is one of the isotopes. When I see normal carbon written like that, that means these numbers come from all the weighted isotopes of carbon. There's carbon-10, there's carbon-11, there's carbon-12, there's carbon-14. There's all these different isotopes, okay? So, you know it's an isotope when you see it either written like this, or this. And of course there can't be just one way to write an isotope. There can be multiple ways of indicating it. What this means is that this is a carbon with 2 more neutrons than normal. Okay? Because a neutron will bring the weight up, but won't change the atomic number. Now, there are things that these unstable isotopes will do to try to stabilize themselves, and it usually has to do with trying to adjust the number of protons or the number of neutrons. There's 5 different ways that they try to do it. The first type of energy that they can give off is called an alpha particle. It is a helium atom. Okay? And this is alpha. Can also be indicated by the little fish. When, for instance, carbon-14 undergoes decay, or undergoes alpha decay, that's the way you would see it written, alpha decay or decays to produce an alpha particle, what else does it produce? When you are balancing nuclear equations, as our nuclear, as President Bush used to say, remember the first law of thermodynamics, what goes in's got to come out. Up here, the numbers here and here have to add up to equal, and down here. So if I've already got 4 and 2 over here, then what's left is 10 and 4. Right? What element is element 4? Beryllium.
Yeah.
All right. So what this would read, how we would read that is to say, carbon-14 undergoes alpha decay to produce beryllium-10. Yes.
So what you do, you have to subtract the atomic weight of the carbon and the atomic number of the carbon from the atomic weight of the helium.
Or you subtract this from this to get that.
Okay.
And it depends on which side it is. You could also say carbon-14 is bombarded by an alpha particle. Bombarded means it's going to be reacting with it. So usually if it's bombarded, it's on the reactant side. If it's decay, it's on the product side. All right. So it could be bombarded by an alpha particle to produce an element 8 is oxygen. The two sides are going to equal. no matter what's going on. The top numbers are all going to equal, and the bottom numbers are going to equal. So this is decay. This is bombardment. So anytime you see a number change by 4 on the top and 2 on the bottom, for instance, if I did, let's see. If I've got something undergoes alpha decay to produce lithium-7, or just lithium in this case. Lithium is element 4, right? Element 3. What was the original material?
Would you add the two to find out what it is?
Yep. So 7 and 4 is 11. And that really doesn't matter. The atomic weight doesn't matter. The main thing is the protons. 3 and 2 is 5. Element 5 is
1.
1. Remember, the protons are on the bottom because these are isotopes. So anytime you see something change by 4 and 2, it's alpha decay or alpha bombardment. And this is the way the sun works. Sun has 2 hydrogens, it takes hydrogens, puts them together, and forms an alpha particle, or helium. Okay? So that's alpha. The next one is beta. Beta. Bless you.
Thank you.
Which is indicated by, bless you,
Thank you.
that, or by and what happens in beta? If we think about a neutron, or if we think about a proton, okay, we've got an imbalance in the neutrons and protons, right? If we think of a proton, or no, let's do a neutron. If we think about a neutron, neutrons are neutral charge, right? On a subatomic level, they really have a plus and a minus particle inside the neutron. So if I've got an excess of neutrons, what I can do is split my neutron, and I'll have a positive particle, which is a proton, and a negative particle, which is an electron. But remember, I'm in the nucleus. Electrons won't exist in the nucleus. So what happens is it spits that electron out. And when it does that, that's when it emits beta radiation, or beta electromagnetic radiation. All right. So I've got an imbalance of my protons and neutrons. I'm going to take a neutron, keep the positive, spit out the negative, like we do in life. All right. So if I am something like, let's do carbon again, and I undergo beta emission, I'm also gonna undergo transmutation and turn into something else. Remember, this is a negative number, so what am I gonna have on the bottom over here to equal 6 here? 7. And then my weight is not gonna change. Why doesn't my weight change?
It was 0 and 14, so.
But why?
nothing's being changed.
Because you still have them.
Because I took a neutron and split it into a proton and an electron. Proton and an electron. Protons and neutrons weigh the same. So while I took out a neutron, I added back a proton, so my weight won't change, but my atomic number will because I've destroyed a proton. Right? And then what's element 7?
Nitrogen.
So an example of this would be carbon-14 undergoes beta emission to produce a beta particle and nitrogen.
So this is called beta emission.
And usually with beta, it's going to be an emission. Not so bad. Then we've got gamma. Gamma is indicated by an upside down fish. Gamma, while we treat it by itself when we're balancing equations, usually will occur with alpha or beta emission. Gamma is special because there's no transmutation. Meaning what you start with, you're going to finish with. Now you might see an asterisk indicating that it is gamma emission. So for instance, if I have, let's pick something fun. Hello. Say we do something like this. Okay. Now, here you may see a lowercase m or an asterisk, one or the other to indicate that it's gamma emission. But overall, you know it's gamma because there's been no transmutation. So the particle here would be, and you don't have to put those zeros, you can just put the gamma sign. So there's no transmutation with gamma. But gamma is usually with the alpha or beta. But I won't have you balance them both. Treat them separately. Okay.
When did
the gamma. Gamma radiation we're being bombarded with every day. I mean, it exists, it is. And it just doesn't we don't undergo any transmutation. Our cells or chemicals don't undergo any transmutation until you become David Banner, apparently. Because when he transformed by gamma radiation into the Hulk. So. And that's, when I talked about naturally occurring isotopes and a lot of the elements up to like, I can't remember if it's 90 or 93, somewhere around in that area, have naturally occurring isotopes. I think I was telling you yesterday, the reason that the core of the Earth is hot and molten is because of the heat produced by these naturally occurring isotopes. And they're radioactive isotopes. So, I mean, it's all around us. We're getting cosmic radiation from space. We're getting bombarded by alpha particles and beta particles and gamma particles and positrons and well, there is antimatter, but we don't get bombarded by antimatter, thank God, because we'd explode. So it's out there. This is just how we kind of explain it. Gamma will go all the way through you, and it can cause cells to transmute. This is why they use, I can't remember if it's gamma radiation that they use. What is it that they use to treat, which kind of radiation is it they use to do chemo, or to do radiation for cancer patients? Do you remember?
What type of radiation?
Yeah, because alpha and beta, alpha will penetrate skin, but will not attack cells. Beta will get a little bit deeper, but you can protect yourself with thick clothing from beta. Gamma will go all the way through you, and it's the one that you have to have the lead aprons to wear and all that. So I think that's what it is.
I think it would have to be gamma.
Yeah. X-rays are actually a type of radiation. They just happen to have the frequency and the wavelength that they'll penetrate your skin, but they'll reflect off a bone. They're not strong enough to go through bone. And that's why we use it to do it. That's why we use it to see if we've got broken bones. And that's why another reason why they monitor how many, you can't go and have 100 X-rays a year. It's radiation, and you can start transmutating your cells.
I think because you have to have, like you wear this badge,
Mm-hmm.
and you can only do a certain amount of radiation. X-rays within a month.
Yeah. And that's the same thing with the nuclear medicine that you're thinking about going into. Exposure, prolonged exposure, or even, when I say prolonged, I mean like hours, any cells that are active and splitting can be affected by that, and it can stop it. So it can kill sperm, it can kill cancer cells, it can kill healthy cells that are splitting. It's dangerous. Useful, but dangerous. All right, so that's the third kind. The fourth kind is positron. Well, it is kind of a transformer. Positron is where you're taking the same kind of thing. Again, you've got an imbalance in your protons and your neutrons. Now, a proton, if we think about it, is a positive and a neutron. It's a positive particle and a neutron. So what happens in positron emission is you've got a positive, kind of a positive electron that is spit out. and then the neutron stays in the nucleus. So what you would see with positron emission is that. And then what else would you have? What else?
Would it be?
What is it transmuting into?
9, because it would give it a plus 1 with a 6. So
Right,
it would be
but,
7.
no, this would be 5. 5 and 1 is 6,
Oh,
and 14, so what's element 5? 4. The two sides have to equal. Okay,
It's a positive
It's a-
electron.
it is a positive electron. It's matter, what positron is actually antimatter. If a beta particle and a positron would get together, there'd be a buttload of energy produced, because that's matter and antimatter, really. Like on Star Trek, when they had the antimatter, the energies ran off of antimatter, I mean, the engines ran off of antimatter, right?
In the little capsule that they're
Yeah.
holding in their hand?
Yeah.
Yeah.
Yeah. That's what they're talking about there. Photon torpedoes. When they talked about, I know, you get tired of me talking about this. Ray Bradbury was ahead of his time. Photon torpedoes. A photon is actually any packet of electromagnetic energy. It's the smallest component of electromagnetic radiation or electromagnetic energy.
You mean Roddenberry, or what are you?
Gene Roddenberry.
Okay.
Did I say Bradbury?
Yeah, you said Bradbury. I was gonna
He
ask,
was
what
ahead
are
of his
you?
time too.
Yeah.
So, you know it's, do what? What? So, you know it's positron emission if it's that. Okay. Then the last one is called electron capture. Now, electron capture what happens in electron capture is you would have a beta particle, but it's going to be on the product, on the reactant side. If it's beta emission, it's on this side of the arrow. If it's electron capture, it's on this side. So what it's doing is reaching out. You've got, again, an imbalance between protons and neutrons. The proton is reaching out and taking a spare electron from the outside and sucking it into the nucleus. If I have a positive and a negative together, I'm creating a neutron. So my weight doesn't change, again, because I've sacrificed a proton and combined it with an electron to produce a neutron. But I've got an electron, I'm losing an electron. So if I had, again, carbon-14 here, and it underwent electron capture, what would my product be? It would be 14, 5, and element 5 is?
Boron.
Okay, so, what does all this mean? All right, for instance, on the worksheet that I handed out, if I've got cobalt, and I'm undergoing what kind of emission?
Beta.
Beta emission. what did I transmutate into?
Element 28.
And I have 60 on the top because my weight's not going to change. And have element 28 on the bottom. Is that nickel? So what I would say is cobalt 60 undergoes beta emission to transmutate into nickel. All right, so the next one. Oxygen, and I'm transmutating into fluorine. It's going to do beta emission. Now you can also have particles. It can also, you can also be bombarded or emit neutrons and protons. And you might see a proton written like this or like that. So this is a neutron, and this is a proton. So for instance, on the next one, I've got a neutron and I'm bombarding uranium-235 with it. And I'm going to produce 10-131 plus something plus 2 more neutrons. So on this side we've got 236 total. And on the bottom we've got 92. Over here, this is just like an algebra where the coefficient is multiplied. So I've got 131 plus 2. So I've got 133 on the top. And on the bottom, I've just got 50. So what's left? I'm going to subtract 92 and 50. So that's going to be 42 on the bottom. And 236 minus 133 is going to be 103. What element is element 42? Molybdenum?
Yeah, sure.
MB?
Yep. Oh, it's MO, sorry.
No, molybdenum. So now the two sides add up, 236 and 92 here, 230, yep, 236 and 50 and 92 over here. Not so bad? Just don't think about it, yeah.
Right there, where the 2 neutron is,
Uh-huh,
I see that you added to the 131, correct?
yes, added 2 to, 2 times 1 is 2, so I added 2 to the 131.
So why did you add it to the 50?
Because 2 times 0 is,
Oh, well.
okay. Now, neutrons and protons can either be used to bombard or as part of the decay or emission. So then when we get into the word problems, first word problem on the second page, on the back page. We've got bombardment, that means we're adding 2. Aluminum 27 by alpha particles. All right, let's write that. We've got aluminum 27, and we know it's aluminum, so it's element 13. We're bombarding that with an alpha particle, and we know an alpha particle looks like this. And we're producing phosphorus 30, what's the atomic number for phosphorus? 16 or 15?
15.
And another particle. Well, what else are we producing? Over here we have 27 and 4 is 31. And 13 and 2 is 15. All right, so we know down here we're going to have nothing because we've already got 15. How am I going to get 30 to 31? Plus 1. So what's the symbol for, what does that represent? Positron.
Say it again?
It's a positron. Don't think it can be. Because it doesn't change the bottom by any. It changes the top.
On the worksheet, do you have the positrons as in?
And that's a neutron. Same thing, I guess.
Okay.
I'm sorry. I'm so telling you wrong, that's a neutron. Positrons are 0 plus 1. Always gotta do one backwards. So it's a neutron, not a positron. Positrons are 0 plus 1. Just like beta is 0 minus 1. Thanks. Alright? Does it make sense? Kind of, sort of? Alright. We'll go over the rest of the worksheet tomorrow. So, the other thing we have to worry about, or not worry about, but the other thing that we're interested in with radioactive material is the half-life. And if you'll look at $542. We have naturally occurring elements, or radioisotopes, up to element 9040. After that, we started synthesizing. Now, most of the ones that we've synthesized, that human beings have synthesized, are fleeting. They have very short half-lives. Some of them we don't even know, we haven't really confirmed that they exist other than that we've seen the energy pattern from them. But if you look at uranium-238, one of the things they use in nuclear energy, look at that half-life. 4.5 times 10 to the 9th years. That's the one I was talking about yesterday. What that means is, if I've got 10 grams of that material, in 4.5 times 10 to the 9th years, I'll still have 5. Then another 4.5 times 10 to the 9th, I'll have 2.5. That's what half-life is how much time it takes for half that material to go away. And like I said yesterday, with half-lives, that means it doesn't ever really go away. And I don't know if you noticed in the video yesterday, they said when these guys were working on Chernobyl, that they were safe, relatively, because the dosage that they were getting was under the amount that they considered safe. Like the firemen I mean, they knew the guys that were in the plant were, but the firemen and the rescue people that were coming in, they said, it turns out now that we have learned that that was 1,000,000 times a safe dose. So again, we don't necessarily always know what we're doing or what we're dealing with. And if you could think that, I mean, the first nuclear material, or what was considered the nuclear material, was discovered by Madame Curie. And that wasn't that long ago. And then we didn't learn how to harness it until the 1940s, 1930s, 1940s. Again, when my parents were alive. So we're dealing with new technology, and we really don't know what we have. And we're burying all this stuff under the Earth's crust. Now, if you think about it, it makes sense to kind of bury it because there's radioactive material under there anyway. But if we're taking synthetically produced radioactive material and burying it where there's naturally occurring radioactive isotopes, do we really know what's going to happen? And do we really know what's going to happen if there's seismic activity out in New Mexico? And then if that caldera underneath Yellowstone goes off, not only are we going to have all that seismic activity, but now we've got the radioactive material that's being released because there's not a drum out there, meaning a drum that we store chemicals in, that's going to last 4.5 times 10 to the 9th million years. Or 4.5 times 10 to the 9th years. Alright, so if we did something like the iodine I was talking about, the guy my friend was exposed to, if it has a half-life of 8 days, and he was exposed to, I don't know, 50 grams, how much would be left after 24 days? Alright, so if we've got so at day 0, we've got 50 grams. So if I go, and every 8 days, it's cut in half. So day 8, we're at 25 grams. Day 16, we're at 12.5. So day 24, 6.25 grams. Or this would be 100%, 50%, 25%, 12.5%. And I said something, most of the, I think they consider most stuff safe at 0.3%. So how long is it going to take them to not be radioactive anymore? Well, in another, after 32 days, he'll be down to 6.25%. 40 days, he'll be down at 3.175, 125.
What's happening when it's decaying? Like,
it's stabilizing itself. It's going through one of those reactions, either a beta or an alpha.
Okay, so it's not just like evaporating or.
No, it's because what happened, they're unstable. These radioactive nuclei or radioactive isotopes are unstable. So what it's doing is undergoing reactions to stabilize itself, but it still, half of it still exists.
Okay.
This is also how they do the carbon dating. For instance, they know that something that existed, carbon-14 has a half-life of 5,345 or 5,435 years, something around 5,000 years. And they know how much carbon-14 material should have that was that old. And then they measure the amount of carbon-14 that's in something and compare it to that. So if it's X amount, then that means it's gone through this much decay and it's this old.
Pretty cool.
It is pretty cool that they can do that. And then for stuff even older, they use the uranium-238, the uranium-238. That's how geologists date rock. They measure the amount of the uranium-238. That's how they figured out that the Earth is about 4.5 times 10 to the 9 years old. And how they were able to tie in that the moon is the same age as the Earth. Because of the amount of uranium-238, active uranium-238 that's still measurable in the rocks on the moon. I think this stuff is fascinating. It scares the hell out of me, but I think it's fascinating.
I want to know who thinks they're that good at chemistry that, you know, I mean.
Hey, they do it all the time. And the new stuff that they use, like the PET scans, the PET scans, they use, do you know what they use? Let's see the book.
A friend of mine's mom is going for one today, and
Is she?
yeah.
She had cancer, or?
Yeah, they just found.
Yeah, so they're seeing how far it is.
Yes.
It uses positron emitters, such as carbon 11, oxygen 15, nitrogen 13, and fluorine 18. That's what PET is. Combines with substances in the body, such as glucose, and used to study brain function, metabolism, and blood flow. As positrons are emitted, they combine with electrons to produce gamma rays that are detected by the computerized equipment. So that's how a PET scan works. It amazes me. I mean, I remember my uncle was one of the managers at Oak Ridge. And Oak Ridge was where they first, if you watch the movie Day One, they actually are at Oak Ridge. The plant is just being built in the 40s to produce uranium and plutonium for them to use in the atomic bomb. And you know how far Oak Ridge is from here? About 9 hours. Oak Ridge, Tennessee. It's about a 9-hour drive. If that plant went, we'd be at least mutated, if not gone. But the nuclear power plants, for sure, if they went, the ones out of South Georgia, if they went, we'd be toast.
So what's the solution? Move to Montana?
No, they've got, Montana's got a big ass caldera underneath it.
Here's Ohio then.
Alaska.
Alaska's got the damn pipeline. This is the depressing chapter. I mean, we've got to think about, and we'll go into, well, there's fission and fusion. Nuclear fission, nuclear fusion. Nuclear fusion, if we could get it to work in an economical way, is really the answer. But right now, how many of you have heard of the particle collider?
CERN or?
There's one in CERN. And they did.
The Large Hadron Collider?
And then there's one
Switzerland.
in Switzerland.
That's the Large Hadron.
Have they got it back up yet?
Yeah, they just found the Higgs boson.
That's what I thought. Was that there? I haven't had a chance to really read about it.
That's the Large Hadron in Switzerland.
So what they do, this sucker, is like, it's a plasma field, isn't it? That they circulate it through. It's a big circular track.
Well, they shoot it down a thing and they collide them, and then they take pictures and readings right when they collide.
But they have to put them in this plasma field that's about the size of a football, or is it 3 football stadiums? So 300 feet. And it has to be heated up to like 1,000,000 degrees in order to get these things to, I mean, they start spinning them and heating them up for them to collide. And when they collide, they produce a lot of energy. Now, this is what I was talking about earlier. This is the way the sun works.